Well, first and foremost, you need an experienced set of logic and circuit designers. And that's exactly what we did. We assembled a top-notch set of experienced circuit and logic designers. All of them had experience doing high-performance and high-integration microprocessors that were built on leading-edge technology. Second, we put together a very thorough verification plan. In the x86 processor world, the nature of the architecture and the nature of this type of a design, where we're doing out-of-order speculative execution, requires very thorough verification. Without a good, solid verification plan in place, we wouldn't have been able to achieve fully functional silicon on the first tape out. Another key skill that was needed was understanding the process and its relationship to the static timing analysis methodology. In particular, we needed to make sure that we modeled the transistors and the interconnect as accurately as possible to take into account all the submicron effects. This allowed us to hit our frequency target, and the frequency of the processor is extremely important to the bottom line performance. This was done using state-of-the-art floor planning tools. And this aggressive floor planning allowed us to achieve a small die size that enabled us to compete effectively in the x86 market. Last but not least, cooperation was a key element. This type of project is much more than just hardware and software co-design. What's required is a multidiscipline at all levels of the company. And so we had to have extremely close cooperation between marketing, the design, production, product test, and even distribution of the product. One of the key elements was managing the design complexity. What this means is opting for simple solutions wherever possible and not compromising the performance. In order to determine the performance trade-offs, what we did is we developed a highly accurate trace-driven model. We obtained many segments of traces from large benchmarks as well as applications, and these included both 16 and 32-bit Windows code. We ran these traces through the model and verified different microarchitectural features to determine what their contribution was to the bottom line performance. In addition, we used this trace-driven model to do detailed instruction-level analysis of which instructions were performance critical and which ones weren't. Those that were performance critical, we implemented directly in hardware as fast as possible, and those that were less performance critical, we used RISC-86 ops in a ROM-based op sequencer to implement them, and they obviously executed slower. Another key element was functional verification. At every level of the design, we assumed that things were not correct until they were verified completely. This was done from the very high-level instruction set all the way to the basic cell that had the gates inside. And at each of these levels, we verified. Without verification, the project would not have been able to be completely functional on first silicon. Another key element in the design philosophy was our implementation approach. We chose a cell-based methodology where we had a set of libraries, a standard cell library, a restricted cell library, and a custom library. The majority of the design was implemented with our standard cell and restricted cells. In certain key areas like the RAMs and the register files, we used the custom approach. This allowed us to implement a very accurate timing analysis methodology, as well as it gave us the capability to iterate very quickly